This is the evaluation of a definite integral using the Python interpreter that comes by default in the Raspberry Pi. This Raspberry Pi has been freshly re-imaged, and I noticed in passing that we had a built-in C compiler and a Python interpreter. And also they also have a very nice editor called Genie under programming, so that's what we're going to use. This integral comes up in the study of dipole antenna, specifically the half wavelength dipole antenna, and it's covered in a different video in this series. So for this numerical integration, we're going to start like with any Python program telling the program where the interpreter resides. In this case, user bin. We're going to import the math library. We're going to get 3 values from the user. Upper limit, which is the upper limit of integration. Lower limit. This is the input statement to actually get this value from the user. And the number of subintervals. Or number of rectangles. We're going to go ahead and initialize our variables. That's our main variable there. That's the function evaluated at the lower boundary, lower integration limit. And we initialize the function evaluated at the upper limit of integration. Next, we're going to go ahead and simplify a little bit of our nomenclature from the math library. Here we're going to actually evaluate the function at the lower limit of integration. And here we're going to evaluate the function at the upper limit of integration. We'll get to copy and paste the function in just a moment. Next we define the step size, which is equal to the difference in the upper limit to the lower limit. Divided by n. And once we have that, we're ready to start our for loop. We do a typical for loop in which we say for I in range, say the for loop starts at 1, goes to n, and steps every 1. And then per the syntax of Python, we put a colon, not a semicolon, so heads up. Then the other thing about Python, we do tab here. And per the algorithm called the Trapezoidal Rule, we go ahead and do what we're going to be doing here. And now we evaluate the function at k. And see if we can go ahead and remember the function there. That's good. And we might as well, since we have it in the clipboard, we'll go ahead and paste it up here and up there. And of course what we'll do is we'll replace this k here with lower limit. So we're evaluating the function at the lower limit of integration here. And similarly we do here the upper limit. Next, we go ahead and do the integration, sum. Why we use a factor of 2 here is how the trapezoidal rule is defined. Next, we go ahead and increase our counting variable. And now we do the final summation per the trapezoidal rule is equal to the function evaluated at the lower limit of integration plus the summed integral or the sum variable called integration up there, which are the rectangles that we've defined, and then the function evaluated at the upper limit of integration. Multiply that time step size divided by 2, and we're ready to print our results. Now we go ahead and save, and in the Genie editor we go ahead and tell it to put it in a particular folder that we want, and we replace the existing name, and that's fine. So now Genie has this little paper airplane which we click, and we should be running our program. So we're going to evaluate this integral from 0 to pi. So the upper limit of integration is 3.14159. The lower limit of integration is 0. But if we put 0 here, identically 0, the sign of 0 is 0, of course. Since it's in the denominator in our expression, it's going to blow up. So what we're going to do is put something very close to 0. And the number of subintervals, we can put 10. And then we get a value of 1.2189, etc. The answer for Wolfram Alpha is 1.2188. Also, another online integral calculator shows us 1.2188, etc. So that could be due to the fact that we've only got 10 rectangles, 10 subintervals. So without changing anything, we can run our little program one more time. Same upper limit of integration, same lower limit of integration, but now the number of subintervals is going to go to 1,000. So now the interpreter is telling us the response, so the answer is 1.2188, etc. That is exactly what the online integral calculators are showing. So this is a quick display of how we can actually do a quick numerical integration, which is very useful, and it does not take that many lines of programming. And again, this is using the Python interpreter that comes by default installed in the Raspberry Pi. So this has applications to the theory of the half wavelength dipole antenna, and it's of interest to amateur radio enthusiasts. Hopefully this was helpful.